So, welcome everyone, and thank you for attending our session, a deep dive into container security on AWS. We are very happy and excited to be here at AWS Reinforce and to talk about container security. In this session, we'll dive into container security layers such as namespaces and SecComp, while teaching you how to configure those security layers to our specific use cases while minimizing risk on AWS. OK, first let's share a little bit about who we are and what our role is at Palo Alto Networks. So my name is Aviv. I am a research team lead at Prisma Cloud, our security solution for cloud environments in Palo Alto Networks, and I'm specializing in container and cloud vulnerability research. In my spare time, I enjoy exploring nature by hiking with my dog, Lizzie.
Hi, and my name is Daniel Prismant. I'm a senior principal researcher at the Prisma Cloud core research team. I specialize in low-level reverse engineering, exploitation, containerscape, and other things in this area. I actually started in the cloud by reverse engineering Windows containers, which was at the time new. Windows containers are obviously on Windows, which is not open source, so they required some skills of reverse engineering. I found my first containerscape on Windows, and that's how I got into the field. I love driving, hiking, and reverse engineering video games in my spare time. In the small picture on the right, you can see me missing the apex in my ND2 Miata.
All right, thanks, Daniel. OK, so with that introduction, are you ready to learn about securing your containers and cloud-native applications with Prisma Cloud by Palo Alto Networks? OK, then, let's begin. We'll first start to talk just a little bit about Palo Alto Networks, and then we go to the container security layers. So at Palo Alto Networks, we have built 3 truly best-in-breed platforms that natively deliver integrated best-in-breed capabilities. Our best-in-breed platforms simplify and consolidate security everywhere it is needed, across networks, across clouds, and across endpoints. For instance, our software next-generation firewalls protect your applications and provide network security for AWS in hybrid environments, stopping advanced cyber threats in real time with cloud agility. Our Cortex SOC allows you to stop attacks with proven endpoint protection and lightning-fast incident response. And today, we look at our application and container protections with Prisma Cloud, our cloud security solution. When put all together, our Palo Alto Networks platforms help secure the majority of the world's most valuable organizations, including all 10 of Fortune Top 10 and every sector, including industrials, manufacturing, utilities, healthcare, and many, many more. In addition, our world-class threat intelligence supports and enhances the security capabilities in all of our Palo Alto Networks products. As we continue to grow our intelligence through our own Unit 42 research team and through incident response work with clients, we continually improve our products.
OK, so let's take a look at now at container security specifically, and how containers can be effectively used to manage risk and business outcomes. Linux containers are a lightweight form of operating system virtualizations that allow you to run isolated applications and services within a single Linux host. Containers provide an environment where applications can run with their dependencies, libraries, and configuration file bundled together. They offer a consistent and reproducible runtime environment regardless of the underlying infrastructure. Start with some container advantages, isolations. Containers provide process-level isolation, ensuring that applications running inside them are separated from one another and from the host system. This isolation enhances security and prevents conflicts between different applications. Another advantage is portability. Container images are self-containered and can be run on any Linux system with the container runtime installed, regardless of the underlying infrastructure. This makes it easy to deploy applications consistently across development, testing, and production environments. Scalability, rapid deployments, and scalability, actually. Containers can be started and stopped quickly, allowing for rapid application deployment and scaling. They also facilitate horizontal scaling by easily creating multiple instances of the same container image. And lastly, efficiency. Containers have minimal overhead compared to traditional virtual machines, since they share the host system kernel. This enables higher density and efficient resources utilization, allowing for more applications to run on a single host. Let's talk about how containers are secured. This will be briefly discussed in this slide, as I will get into more details later about each one of these features individually. First, it is important to note that containers are not a Linux feature. Instead, there are numerous Linux kernel features that enable containers to exist. Namespaces isolate and virtualize system resources for a collection of processes: process tree, network stack, and mounted file system, and more. This is the most important feature. The next one is Cgroups, which allow processes to have limited resources, such as CPU time, system memory, network bandwidth, and more. Next one is capabilities, which divide the privileges traditionally associated with root or unroot into distinct units. And lastly, SecComp, which allow processes to make a one-way trip transition into a secure state.
All right, thanks. So those kernel mechanisms or container security layers that Daniel just mentioned create some limitations for containers, and therefore certain operations are restricted by default as a security measure to prevent unauthorized or potentially harmful actions. And that is fine, because we do want our container to be isolated and secure. But how limited are they? Let's take a look. So one classic example of these limitations is the mount operation. By default, containers are designed to have limited permissions to file system operations due to the potential risks associated with file system manipulation. Without such restrictions, a malicious entity or application inside a container could mount or unmount file systems, potentially causing data loss, service disruption, or enabling further exploitation. Similarly, another potentially sensitive operation is loading a kernel module, as this kind of operation allows to load code into the kernel, which would be executed with highest privileges on the host machine. So this means that if attackers compromise a container, then they would be able to break out of the container and compromise the host by loading a kernel module. There are many more operations that are restricted by default, and having restricted operations translates into having restricted use cases. For example, if you would want to deliver a monitoring or security tool that require high privileges in a container, then you won't be able to do so because you will lack the privileges by default. Same goes for example, advanced networking tools that require executing some system calls that might break the container isolation, or for running Docker inside Docker, which sounds pretty funny, but could be very useful for very specific use cases, such as having a containerized honeypot system that is based on Docker, while having Docker as one of the honeypots inside.
OK, now let's take a look at how developers can obtain risky and elevated permissions for their containers. DevOps teams utilize containers more than ever today, but securing them is often an afterthought. Containers privileged mode is a feature in containerization platform like Docker that allows a container to have elevated privileges and access to the host system resources. When a container runs in privileged mode, it bypasses certain security restrictions and gains almost the same level of access to the host system as a process running outside the container. Take a look at the diagram on the right. It represents accurately what privileged mode does. Instead of the containers being isolated, the privileged container can reach and has access to not only the container runtime, Docker in this case, but also to the underlying host. Here are some of the things that a privileged container can do, just to give you an idea of how risky it is if not used properly. So a privileged container can mount the host file system. It can add a user. It can add an SSH key. It can add a cron job. It can even load kernel module, which will usually be game over in terms of security. Privileged containers underscore the need for cloud users to take a defense in-depth approach to securing their cloud infrastructures that includes continuous monitoring for threats and misconfigurations. The first risk is obviously a container escape. Personally, I feel like moving from privileged container to the host and escape is pushing it, as running inside a privileged container is basically as running on the host. The difference, and the reason I listed the container escape here anyway, is because many people, even professionals, run in containers in privileged mode without fully understanding the security risk it carries. One of those risks is a node takeover, which is usually when a container escape is mixed with something like Kubernetes or maybe a serverless platform. The attacker that escaped the container can now take over the entire node and maybe all the other resources associated with this node, such as other containers. A cluster takeover is the next step from a node takeover, and will usually require some additional vulnerabilities in the cluster for that one vulnerable node to be able to take control over the entire cluster. And data breach and denial of service, two additional risks of container escape. Now a little bit of story time. Siloscape, which was a malware that targeted Windows containers in order to leverage an unfixed vulnerability that enabled an easy container escape. The malware then took over the node, and in some of the cases, even took over the entire Kubernetes cluster. So it focused Windows containers in order to break out to the node and then take control over the entire cluster, taking control over all the other resources, not only the Windows containers. And when we found Siloscape, it had dozens of Kubernetes clusters, entire clusters under its control.
All right. So in some cases, our containers would need to have extra privileges. So how can we grant them those extra privileges without using the privilege mode and while minimizing risk? So that's basically the talk. So this might sound pretty straightforward, but the solution is to use the principle of least privilege. Or in other words, instead of just granting your container privilege mode, we should manually configure security layers such as seccomp and capabilities for each container so that it will have the minimum required privileges, and by that, we could minimize the risk. In order to do so, we would need to follow 3 steps. The first one is that we need to understand container security layers, because if we want to configure something, we need to first understand it. Then we need to determine the minimum extra privileges that the container needs. And now that we know what are the extra privileges that we need, we could configure fine-grained security layers with the minimum required privileges and apply them to our AWS deployments. All right, let's talk about container security layers.
OK, let's do a drill down and take a deeper look to all the different security mechanisms that we discussed earlier. now in depth. So the first one is Linux capabilities. Linux capabilities are fine-grained privileges model in the Linux kernel that allows process to have specific privileges without needing full root access. Traditionally, the root user has complete control over the system, but capabilities provide a way to divide root privileges into distinct units, granting different privileges to different processes. In the context of containers, Linux capabilities play a significant role in enhancing security by reducing the attack surface within a container, rather than running a container of full root privileges, which can be security risk if compromised. Capabilities allow for more granular control over the privileges available to containerized process. When a container is created, it is isolated from the host system and given its own set of capabilities. By default, for example, Docker and other containerization platforms drop most capabilities from the container's initial set, providing restricted environment. This means that within a container, processes do not have the same capabilities as the root user outside the container, even if the user inside the container is root. So for example, a container might need to bind to a network port below 1024, but does not need any other root level privileges. Side note, binding a port below 1024 requires root privileges. In this case, the CNAPP bind service capability can be granted to the container, which will allow him to bind the needed port without having full root privileges. CNAPP, which is a short for secure computing, is a Linux kernel features that you can use to restrict the system called process can make. This is especially important container environments such as Docker or Kubernetes to increase security and reduce the attack surface of the containerized application. In the context of containers, CNAPP provides an additional layer of security by allowing you to define a profile that lists the allowable system calls for a container. If a process within the container tries to invoke a system call not on the list, the kernel will block the call and will terminate the process. This can help prevent potential security vulnerabilities. For instance, if an attacker manages to exploit a bug in your application and tries to invoke a harmful system call, they would be thwarted by the CNAPP policy. So for example, a system call, a vulnerable system call was found and was reported by some other security researcher, and your container has access to this vulnerable system call. By default, if not using CNAPP, an attacker would be able to leverage and exploit this system call, even if your container never used that system call. But if using Docker default CNAPP profile, that won't necessarily be the case. Docker might block that system call, and it won't be able to be exploited. Like I said, the default CNAPP profile used by Docker, for example, already blocks a significant number of dangerous system calls. Before moving on, I want to touch briefly on the difference between CNAPP and capabilities, because it can seem that they do the same thing. Capabilities involve various checks in the kernel function reachable by system calls. If the check fails, the system call is typically made to return an error. The check can be done either at the beginning of the system call, maybe at the middle of the system call, maybe somewhere else. CNAPP is a system call filter. The system call won't even be executed if the system call isn't allowed by the CNAPP profile. Let's talk about Cgroup, which is, in my opinion, the simplest to understand. Basically, resource management. Isolation. Process running in the container can't monopolize all the system's resources. Resource accounting. Mechanism to measure and track the usage of resources by any specific group. Resource control. Allow how much resources each group gets. And prioritization, which is kind of neat, you can prioritize one group of processes over another, ensuring that critical tasks get the resources they need. So even if you don't want to split the resources between all your groups, you can still prioritize one group over the others. Namespaces is the most important kernel feature for container security, in my opinion. It makes a group of processes think that they have their own isolated instance of a global resource. Let's go over them one by one. We have the PID namespaces, which isolate the process ID number space, meaning that processes in different PID namespaces can have the same PID. Net namespace, network, provides isolation of network controllers, system resources associated with networking, firewall rules, routing tables, and more. Each network namespace has its own private set of IP addresses, its own networking devices, its own routing tables, and more. Very useful in regards to container. IPC isolates various inter-process communication resources such as system VIPC object and POSIX message queues. Mount, super important as well, isolates the set of file system mount points seen by a group of processes. Processes in different mount namespaces can have different views of the file system hierarchy. This is the feature that allows containers to be blocked from accessing the outside world in terms of file systems. UTS isolates node name and domain name, which represent the system host name and NIST domains name. Basically allows the container to have its own host name. User, another super important namespace, isolates the user ID and group ID number space, meaning that a process that processes user and group IDs can be different in different user namespaces. This is the namespace that allow a process to have root privileges inside a container, but not outside of it.
Thank you, Daniel. OK, so now that we understand container security layers, let's go to the second stage and take a look at how to actually identify what the least privilege might be for a container. The question in here is, what kind of extra privileges do we need? Executing privileged networking operations, or maybe executing monitoring operations like ptrace, or just having more CPU time or memory? Let's go over to the tools that allow us to profile our containers and understand that. For identifying the required capabilities and second profile, we can use strace, which is a diagnostic and debugging utility for Linux that uses ptrace to debug binaries. By running strace with a command as an argument, strace yields the system calls that were executed. So for example, in the execution over here, we could see that the ls binary was executed and that it used many system calls such as read and write. strace enables us to figure out the required system calls, and with this understanding, we can tailor the second profile for the container. Subsequently, we can correlate the relevant capabilities to these system calls and configure the necessary capabilities accordingly. So with this tool, we can configure both the seccomp and the capabilities. For a smoother profiling process, I suggest utilizing strace within your container environment, which ensures that the profiling is executed as anticipated. This can be accomplished by altering your container configuration and specifically add the strace command at the beginning of the execution command in your container configuration, and then run your container as privileged for a successful execution. To identify the necessary Cgroups, we can use top, which is an open source utility that offers a dynamic, real-time, and interactive view of processes running on a system. Utilizing top allows us to gain valuable insights into our container, such as its CPU usage and memory consumption. And to streamline the profiling process, it is recommended to run top on the host machine with root privileges. This provides top with the visibility into the processes running within the container. Additionally, you should execute your container in privilege mode, and by that ensure it has sufficient resources for a proper execution. The last security layer we did not discuss is namespaces. And as far as we know, there isn't a tool that can show you what shared namespaces is needed. But having a shared namespace with a container is very unique. So in most cases, you would know if your container needs to share a namespace with the host. OK, so now that we know what are the security layers in container, and we have discovered the minimum required privileges with strace and top, let's customize our AWS deployments with the minimum required privileges and minimize our risk. The first example is for EKS. So in EKS, just like any other Kubernetes deployment, you can configure all of the security layers we talked about using the security context parameter. For example, in this case, we have added the netadmin capability, configured a second profile, and limited the CPU and memory consumption with Cgroups. It's important to note that in containers, when you add a capability, it automatically updates your second profile to include the corresponding system calls for the added capability. This allows the execution of the relevant system calls. For instance, if you add capsys BPF, the second profile will automatically permit the execution of the BPF system call. This enables you to run your container without requiring additional modifications to the second profile, which is great. However, a potential issue arises in here, as some capabilities encompass a large number of system calls. Adding such capabilities permits the execution of unnecessary system calls in the second profile, which can introduce additional security risks. For instance, there might be a situation where you would want your container to execute only the unmount system call. So you will add the capsys admin capability, which allows the container to execute the unmount operation in the capability layer and configure the seccomp to allow the unmount system call. However, other than allowing the unmount system call, this capability also configures the seccomp profile to execute other risky operations like mount or setNS, which can pose major security risks. So our recommendation in here is that you need to configure both the seccomp and both the capabilities in order to minimize the risk. Let's talk about ECS. So ECS allow you to configure Cgroups, seccomps, and capabilities just like in EKS. The major difference with EKS is that in ECS, you can only configure some of the namespace parameters, such as the PID namespace or the IPC namespace. Lastly, we have Fargate. Now, it's important to note that Fargate is an environment managed by AWS. So it does not permit the allocation of additional privileges to individual container. This constraint is actually a key aspect of AWS security strategy, as the granting of excessive privileges could potentially open doors to exploitations. So AWS are right on this because it's their environment and they don't want you to break out. All right. So now that we have discussed all of the steps on how to configure your container security layers, let's summarize everything. Here are the takeaways we would want you to take from this talk. First is that sometimes, for specific use cases, containers need extra privileges, and that's fine. But containers with extra privileges increase security risks. So we would prefer not to run containers as privileged, but to run them with the minimum extra privileges they need in order to reduce risk. By tailoring security policies to provide only the necessary privileges, we can allow our container to run with the required privileges while reducing the potential risks.
OK, let's briefly take a look at how we can help protect your cloud deployments with Prisma Cloud by Palo Alto Networks. So what is Prisma Cloud? Prisma Cloud is a comprehensive cloud-native application protection platform, or CNAPP for short. Our application protection platform unifies all security use cases across the life cycle, from development to production. This unified full lifecycle security coverage is what we call code to cloud. To achieve code to cloud security and prevent risk and breaches, Prisma Cloud focuses on 3 security pillars: visibility and control, risk prevention, and runtime protection. To begin, we believe that visibility and control is fundamental to cloud security, and the first step customers should take. This is where Prisma Cloud can help customers answer, what do I have in the cloud? What is broken? What's the most broken thing right now? Help me prioritize. Help me fix things. Tell me the 20 things that I can tell my DevOps team to fix right now. Yes, visibility and control is important first step to better cloud security. We also believe that preventing risk is best done early on the app life cycles. Customers want to be secure by design. So risk prevention, which cloud-native Prisma Cloud does very well, can reduce a lot of pain later on in the development life cycle, and is essential to modern application protection. But also, in reality, we know that the world is not going to get to a place where there is zero risk in production. In other words, it takes time to the world to adapt to the new modern technologies. Also, what could go wrong does go wrong. So runtime protection with Prisma Cloud continues to be a critical area to put security focus and completes our full lifecycle protection from code to cloud. So with runtime protection in mind, let's now talk through some of the impactful ways Prisma Cloud can keep you safe. Let's start with vulnerability management. We know that securing cloud-native application requires a comprehensive view into vulnerabilities across the application lifecycle. With the Prisma Cloud platform, you can manage full stack cloud risk from a single console, prioritize risk across clouds on-premise with intelligent risk scoring, alert and prevent vulnerabilities across all environments, shift left, monitor container registries, and define golden images to integrate security into your CI/CD pipeline. Our continuous proactive and automated checks for vulnerabilities in your cloud environment with prioritized monitoring and remediation help you stay in control of the running cloud and makes it easier to deliver on your compliance goals. And Prisma Cloud helps you achieve compliance at runtime. Our purpose-built controls are designed to help customers gain the required visibility into compliance posture and maintain that compliance. We help customers by delivering both real-time and historical compliance status views for your entire cloud stack. With Prisma Cloud runtime compliance, you can centrally monitor and achieve compliance within a single security solution, leverage 900 customizable compliance checks, PCI, HIPAA, GDPR, NIST, and more. Leverage CIS benchmarks with certified coverage for AWS, Docker, Kubernetes, and Linux. Integrate compliance across the entire application lifecycle. If you are a customer of Prisma Cloud, you gain compliance checks across the full application's lifecycle. This coverage and context help to prevent misconfigurations from ever-reaching production environments, keeping your business compliant and your users and data safe.
All right, and what better way to stay compliant than to codify your compliance governance and enforcement with infrastructure as code? With Prisma Cloud, you can automatically enforce cloud guardrails and maintain compliance across the lifecycle using infrastructure as code scanning and policy controls. You can prevent developers from making ad hoc changes which may add significant risk. Set custom governance levels per repository or per resource. Create custom policies using Python, YAML, or the UI policy editor. Automatically get comprehensive code reviews with actionable guidance for every Prisma Cloud security scans. We know that misconfigurations can happen anywhere in the development lifecycle. With automated infrastructure as code policy in place, from code to cloud, you gain repeatable, fast remediation, and reduce failure rates. In short, infrastructure as code scanning is a great and modern way to significantly improve and control your cloud security posture. And because we know that the cloud is constantly evolving, Prisma Cloud offers agile and integrated controls. This is to ensure your full stack is continuously protected. With agentless security by Prisma Cloud, teams can quickly see security status without the need to install an agent or disturb the execution of your workloads. Prisma Cloud offers the flexibility to use agentless and agent-based protections, whichever best suits your needs. The Prisma Cloud agentless option offers agentless scanning without affecting workloads, quick assessments of cloud risk, including known CVEs, misconfigurations, and other security issues. A perfect solution for evolving and complex workload types, especially containers as a service. It's a straightforward implementation and adoption that can be fully automated, and a unified console and a single policy engine for both agentless and agent-based approaches. With Prisma Cloud, you can remain nimble and gain relevant insights into the health and security of your entire system, helping you to evaluate what needs extra security and what doesn't. And when you do need extra security for your most sensitive and critical workloads and applications, Prisma Cloud automatically defends the runtime to ensure the full stack is secure. With Prisma Cloud comprehensive runtime self-protection, you get unified protection against runtime threats with just a singleton agent. Automated runtime security across process, file system, and network activity, and deep forensics for every audit or security incidents with timeline views and mapping of incidents to the MITRE attack framework. Runtime security is critical. That's why Prisma Cloud by Palo Alto Networks delivers anomaly detections for dynamic cloud environments that supports enterprise scale, hardens environment against vulnerabilities, and enables effective incident response with context-rich findings. And don't just listen to us talk about our comprehensive security platform and how it can help you stay secure. Listen also to many industry analysts and technology research firms who have recognized and validated Prisma Cloud as a leader across multiple cloud security categories. For instance, Forrester, in their cloud workload security wave, positioned Prisma Cloud platform as a leader in CWP. Likewise, their prestigious Frost & Sullivan also positions Prisma Cloud as a leader, this time for the general CNAPP application protection category. And there are many more confirming analyst voices citing Prisma Cloud as a leader in areas like vulnerability management, developer security, policy as code, and CSPM. Listen to our customers. Best in the market, says one reviewer. Another says mind-blowing capabilities. With Prisma Cloud by Palo Alto Networks, you're getting best-in-class security platform that's leading the way to the better and more secure tomorrow.
Finally, let's take a look at how Prisma Cloud has helped customers transform their business on AWS, accelerate their cloud adoptions, and realize all the value they can get from the cloud. In this example, we have Pokémon, a global entertainment and media company who was seeking to adopt to modern cloud security for their popular app. Pokémon chose Prisma Cloud because we helped these customers simplify their cloud security, and Pokémon was impressed with how Prisma Cloud could deliver effective cloud governance and compliance with automation and at scale. With Pokémon global user base expanding rapidly, the company needed its cloud security to keep pace, and Prisma Cloud was brought in to support two new and very modern CWP and CSPM implementations that helped secure their rapid delivery CI/CD pipeline and helped them to ship secure code fast on AWS. With our code-to-cloud security platform, Pokémon was able to rapidly onboard a modern cloud security operation covering the full stack and fully integrated across the life cycle, allowing the company to grow fast and be modernized for the future. As a result, Pokémon significantly reduced its volume of security alerts from 15,000 to only 2,500 through real-time alert reporting and configuration management. Pokémon experienced a 30 seconds onboarding and quickly benefited from simplified compliance operations, taking advantage of our one-click compliance reporting feature. A senior security engineer at Pokémon summed up their Prisma Cloud experience by saying, implementation was an absolute breeze, simply check a box, generate a report, highly beneficial. Pokémon is an example of a global company realizing modern cloud security outcomes at scale by leveraging the Prisma Cloud code-to-cloud security platform. We hope you will also take a look at what Prisma Cloud can do for you. Thank you, everyone, for attending our session and learning more about container security and how Prisma Cloud by Palo Alto Networks helps protect you from code to cloud on AWS.